from Tata Steel. He will be deliberating on illumination and speed invariant steel surface imaging for high-speed rolling mills. Mr. Chitresh Kundu is currently working with Automation Division of Tata Steel as a technologist in the Instrumentation Control Group. Mr. Kundu has completed his Masters of Technology from IIT Kharagpur in RF and Microwave Engineering, Department of Electronics and Electrical Communication Engineering. His research interest includes embedded systems, high frequency physics and electromagnetic field theory and its applications. Now I invite Mr. Kundu, please.
Good afternoon. Today in this presentation, I will be talking about our journey towards the first of its kind, indigenously developed surface inspection system at Automation Division Tata Steel. So, first of all, let us understand what surface inspection system is all about. A surface inspection system, if someone tells me to summarize, I will tell you it consists of an image acquisition part, then there is a defect detection part, and the third one is defect classification and its storage. So, in this talk, I will be mostly focusing on image acquisition, how high quality images are acquired and they are being processed. So, if we see nowadays rolling mills, the coils or the strips, they are moving at very high velocity. So, any high speed image acquisition itself leads to several challenges like motion blur. We will get blur in the images, and then we have to look for the environmental conditions. Then we have to think about how much our camera is responsive for a particular emission. So, coming up with these facts, we thought of using a special type of camera which is known as line scan camera, where the frequency of scan is in kilohertz. It can image on rollers, which is very predominant structure in any steel plants. So it can image at non-flat surface, and then the exposure time is very low, so that to keep the blur at the minimum. So what this line scan camera is, it is basically a single dimensional sensor, and by virtue of the motion of the object, it produces a two-dimensional image. The advantages is, as compared to any area scan camera, the price to pixel performance is very high. Then, due to lesser amount of electronics involved in this line scan camera, will have very high pixel fill factor, and higher the pixel size will get more intense and crisp images. The trade-offs. For operating a line scan camera, we need very good illumination source, and illumination must be uniform. It should be able to produce very high intense emissions, so that during that small exposure it can get sufficient number of photons to get a good exposure. So these two things has been taken care of by our light design, which has been patented. And third is the basic problem with the line scan camera is the vertical resolution, or the resolution along the axis of motion. So if we see, if an object is moving towards a line scanner at normal speeds, will get a good aspect ratio preservation. But as the object moves very fast, will get compressed image. If it is moving slowly, the repetitiveness of this camera will lead to elongated images. See, this is the image of same object looking different. So this will lead to wrong classification of the defects. So how to tackle this problem? So we went to the camera manufacturer and thought, the line scan camera takes square waves as input, where the line period tells us the frequency at which the line is being captured. The on time of the square waves tells us the exposure time, and during the off time it reads the signal which has been exposed. What if we change the exposure time and it falls between the readout? So the frame will get skipped. That is a problem which we can discuss later. So now how to synchronize the camera with the moving speed of the web. So if we see a generalized diagram of a camera optic system, where there is a sensor and a lens with a focal length f, and there is a distance from the field of view. So we can see these two triangles are similar in nature. So from basic mathematics, we can derive an expression which relates field of view to the camera optics. And as I said, line scan camera, the vertical resolution or the resolution along the direction of the motion depends upon the moving velocity. So if I derive those things, if it is the strip is moving with a velocity v and in time t, I can see the distance traveled by the speed must be equal to the horizontal resolution to preserve the aspect ratios. So here from this I can compute the line capture rate should be equal to some mathematical expression in terms of camera optics which is fixed for an installation. So we implemented this thing in an embedded system. We got a microcontroller and we took the speed signal from the class. Then we had fixed the exposure time. Then that's it. We generated a signal for the top camera and the bottom camera. But we faced certain problems which I'll discuss. Due to that, we added some feedback mechanism to the controller and some mode selections so that it can be robust enough to sustain itself in any plant condition. And this design has been patented by us. So how this verification is done? So we have implemented this theory and we can see the mill speed and the line capture frame rate is equally matching each other. And this is the image captured from CRM, a cold roll sheet well point, and we can see that the aspect ratio of the weld hole is preserved. Now, we thought that this is the end of the implementation, but then what we saw that defect detection efficiency is sometimes very good and sometimes it is not so good. So why? We thought so and we got the answer. We captured several images over several months and we saw there is a drift in the gray level of the images. Some images are underexposed, some are overexposed and some are perfectly exposed. So during the underexposure and overexposure, the image information is being lost. So the optimum gray value what we found out for the perfect exposure is 130. And if we plot the histogram, we can see that if we don't have any exposure control, the histogram is widely spread in all the gray value bins. So what we did, we take the reference of the speed of the object, the gray value, that is the feedback from the server, the previous frame feedback. Is it low? Then we will increase it by a certain amount if the target level is higher, and we will decrease it if the target level is lower. And by that virtue, we generated a feedback mechanism which will give me constant gray value for each and every frame. So this is the result for that thing. We kept the target as 130 and we can see over a period of 25 frames it is closely following the target gray value. And now the histogram is much more at its peak and the standard deviation is also very low. It is mostly concentrated at 130. So the mode selection. Mode selection, we have 4 different modes for operating this device. Mode 1 is used for testing, for calibrating the camera against any reference. Mode 2, it is the manual switches which I have talked earlier to have some predefined exposure value. Mode 3 we haven't thought of the use yet. And mode 4 is a mode which is generally being used by the plant condition where due to varying illumination, varying the intensity or the reflectivity of the surface, we can capture constant gray value images. Thank you.
Are you only taking the images or there is a defect detection is also there?
Yes, there is a defect detection also, but defect detection itself is a separate topic. And we have a high-speed image processing platform to detect defect out of the acquired images.
So almost all type of defects which are generally coming from the first treatment is being
It is in cold roll mill.
It is in the cold roll mill. So whatever the possible defects
Yes.
are there, it is all incorporated in there.
Yes.
What is the frame rate of your camera?
See, this is line scan camera. The maximum line rate scan rate is 18 kilohertz, and we have frame size of 2048 lines. So approximately we get something like 9 frames per second.
We put myself of RDCS. we could have done through AES scan camera, but you have chosen line scan camera.
I'll tell you the reason. There are a couple of reasons why we preferred line scan camera over area scan camera. First of all, we saw that the strip flutters during the movement. So what it does, it changes the field of view of the camera. So the best place to keep the camera is on the rollers. And roller is a curved surface. So that way, a line scan along the diameter of the roller can give me flat images. Secondly, what area scan camera will do, it can overlap the frames. If two frames are taken simultaneously, maybe the same object has been imaged twice. So that leads to the decrease in processing ability of the hardware. So this device takes care of that, as well as it gives me no overlap and gives me a higher processing output.
It means you have done on the microcontroller, a lot of software has to be developed.
Yes. It has been developed.
But in case of AES scan camera, and then you have a frame and you have a standard software, but here you have to develop own software.
Yes.
I think so.
Yes.
Whose camera you are using?
We are using camera from DALSA.
Datsun. And these cameras, when they're used continuously, there is very much heat generated in the electronics.
Right.
How you are keeping it cool?
First of all, we have some passive heat sink design for these cameras. And secondly, we ensure that whenever we are placing the camera in the plant, first of all, we are using in cold roll base. So the conditions are not so severe as compared to hot strip mill. So we ensure that the airflow is maximized at the location of the camera installation.
And how you are?
We have some cooling arrangement like
that means you have some vortex cooling system?
Not vortex,
Not
we use certain type of small exhaust fans, that's it. Small fans.
Okay, thank you.
You have top and bottom camera both?
Yes, we have this controller works for the top camera as well as bottom camera. We are imaging simultaneously the top part as well as the bottom part of the
So
sheet.
synchronization part is how it is done? The time stamping or something?
The synchronization is taken by, like, the frame rate is defined and we are getting the speed signal from the plant. So that speed signal is taken to the controller and based on that mathematical relation, it generates that wave. That's how the synchronization is being done. The embedded hardware has got two channels and two separate CPUs. So one CPU is taking care of the top camera and other one is taking care of the bottom one. Any more questions?
No more questions?
You said about one dimension and two dimension.
Yes.
I did not understand.
Shall I get back to the slide?
If it is.
Yes, I'll get back to the slide. You can see this is the line scan camera. It sees only a single line from the object. Whereas this area scan sees an area. It's a single line sensor. So it captures this line only unless and until the object moves. If the object moves, then only it sees the next part of the object which is under inspection, and that's how it generates a two-dimensional image or a frame. This is the thing.
As continuous as possible. That is the meaning.
Yes, it has to be continuous. The motion has to be continuous, but the plant running speed, it depends upon the production rate or something, so it varies. So it can either go from 1 meter per second to up to 6 meters per second. So we adjust our line capture rate according to the speed of the object under inspection.
Okay.
Excuse me, myself from RKSM, JSPL Ambul. This camera is capturing the profile of the strip also, flatness, wavy,
No, the camera is
only surface defect,
yes, it's surface imaging.
only surface image.
It's two-dimensional imaging.
Thank you.
No more question? You want to ask?
Thank you very much.
Thank you.
Now the next session is from Mr. V. Subramaniam from Tata Steel. We will be deliberating on camber measurement of hot rolled strips in steel bands. Mr. Subramaniam is currently working with the automation division of Tata Steel as a technologist in instrumentation and control group. His areas of expertise include artificial intelligence in general, image processing in particular, and their applications to instrumentation and automation. Previously, Mr. Vasant was working in the product development and R&D of fire and gas safety system with General Monitor Systems, Singapore. His key research areas included safety instrumentation and system integration. Mr. Subramaniam has completed his Masters in Engineering from National University of Singapore, specializing in artificial intelligence, and completed his Bachelor's degree from Anna University, specializing in instrumentation and control engineering. Mr. Subramaniam, please.
A very good afternoon to one and all present here. During Mr. Moy's presentation, we had a question on camber measurement system and basically how camber is measured at the hot strip mill. So I believe that this presentation would clarify those doubts. So coming to this system, what exactly is camber? So camber is when you have hot strip transfer bars in the hot strip mills being rolled. What happens is you have different roll forces applied on two different rollers. So what happens is one side of the transfer bar is elongated more than the other. So that creates a longitudinal curvature. And there are many disadvantages caused due to this camber. One is it can hit the mechanical guides, that is the immediate effect. The mechanical guides, the strip goes and hits against it and it creates chaos. And apart from that, the difference in the thickness of the transfer bars, it becomes more and more as the camber is allowed to roll through. So during the 7 passes, it increases gradually, and the curvature increases also. So basically, then we thought of, okay, how do we develop a system for this to measure camber in the hot strip mill, in the roughing mill, in the roughing mill itself. So basically what we had was we found out what are the objectives of a system like this. So first was we needed the strip position and geometry at each rolling step. So during the passes in the hot strip mill, in the roughing mill, what happens is it passes through 7 times. So at every particular pass we needed to find the geometry. Second was how to improve the quality of the coils by removing camber related effects. So that was the key objective of this system. The next is we had to provide an accurate measurement results for the operator to take appropriate control. So he had to make sure the rolling force is adjusted accordingly. And the most important condition was to operate under harsh environmental conditions. As asked in the previous session, we had previous presentation, the environmental conditions at HSM is too harsh. We have high temperature, we have water spraying through, we have dust, and the IR radiation from the transfer bars themselves. So in those conditions, how do we protect the camera itself, and how do we take care of the cooling of the cameras also? So that was the key engineering objective we had to take care. And finally, it has, for any steel plant, it has to be cost effective and easy to implement. So that is always there. Any image processing system, as explained in the previous presentation, has an image acquisition system, and in this case we are using area scan camera. And then it has a computer for processing, and there is a storage for the images to be stored. And then we have an online buffer where what happens is you have images coming through at a very high frame rate, and the processing takes a little longer. So we will have to keep a buffer for the images. And then we finally display the images. This is the system installation which is done in the measuring house of the roughing mill. What we have is we've used a pinhole technology where there is only a small hole of about 3 to 5 mm, and we have a camera which is placed in a 2 meter long tube. So what happens is we'll have to measure the whole transfer bar with that particular pinhole. The major advantage is we will not allow any dust or water particles to come in, and we are protected against the temperature, and the next issue was, okay, now the temperature is taken care of and the moisture and water condensation is taken care of. But we had to cool this camera itself because the electronics produces a lot of heat. So for that case, we have air purging system for this particular tube. So since the measuring house is about 6 meters away from the rolling bed itself, so that way we had to take care of only the tube. So for that we have an air purging system, and continuous air is purged through the pinhole. And another advantage of that is we create a positive pressure at the pinhole. So the dust conditions from outside never come inside. So that way the dust is also taken care of. The installation, another issue was when you use a pinhole camera, you get a mirror image, an upside down image. So that is a thing we had to take care of in the software aspect. So we had to invert the image in the software. So this system, actually we have two advantages in one particular installation. We have a same installation for our OptiCrop system in the roughing mill, where we have cut the heads of the head portion of the transfer bar or the coil rather. And the same camera we use the images for the camber measurement also. Basically the image